Hey, look at that. Am I live? I'm live. Cool. Yes. The ballet dancer is right there. Oh, and I'm supposed to put out, thanks for that introduction. I am Alan C. Smith. This, of course, is Tiny Monster. We've all seen him around. I pretty much don't do presentations without him anymore. Long story about that. Please feel free to ask me in our off time. Hi. I am Alan C. Smith, consulting software architect. I am also a consultant, LabVIEW champion, also a member of the Actor Framework Guild, which is a group of actor framework enthusiasts trying to make AF more accessible to the general LabVIEW community. I am JustACS on the forums, and as you heard, I do also occasionally answer to Don Quixote de la Mancha or the Ingenious Gentleman. So, my daughter's in some of these pictures. Of course, there's other kids in there, so I didn't share those pics, but I thought you'd have fun with that. Let's tilt at some windmills, shall we? I want to take up where we left off 3 years ago, just about the same time in the conference, too, just as we were wrapping up. We had one last session. Those of you who are here might remember this. It was an open mic session, and we were talking, as we always do with these things, we were talking architecture and frameworks, and we had a lot of conversation toward the end that was very much of sort of a back and forth. It was like a tennis match between people saying things like, well, I like DQMH because, as my architecture, because it works better with test stand. Okay. I like Actor Framework as my architecture because I like what it does with classes. And the use of the word architecture in that context really started to bother me. And at the end of that session, I grabbed the mic, and it was just about the last thing that was said, and I said this. I said, DQMH and the Actor Framework are not our architectures. They are frameworks we use to implement our architectures. And that was it. That was it. We all left. We went our separate ways. I left with two overriding thoughts. The first one was, oh, if I say something like that in the last couple of minutes of the conference, I better be prepared to say more when I come back in a year. A year, okay, sure. But that aside, I had this feeling that came over me at that point, which is that, and the thought that popped into my head, and I actually wrote it down in my notebook, was that we were doing something wrong. And on further reflection, it wasn't so much wrong. The things we were doing were basically right, but that we were missing a piece. We weren't emphasizing something that I've come to see is really important in these systems when we think about them, when we talk about them. A lot has happened in what turned out to be 3 years, not one, not least of which was 2 weeks after GDevCon. We were at the CLA Summit, and we were talking about interfaces. Yay, interfaces, right? We were going to get them in LabVIEW 2020. And since then, we've had about 3 years to absorb that new feature and think about it. It's led to a number of things like, I got to rewrite the actor-oriented design in LabVIEW, update it with interfaces. And so I've been thinking a lot about how to teach how to use interfaces in an AF context. And so I thought I'd bring that back as sort of my follow-up to 3 years ago. I want to talk, before I really get into interfaces and what they do for us in AF, I want to talk a bit about architecture and actor systems, that piece that I felt like we were not, I think we all knew it was there, but we didn't talk about it enough. It wasn't enough of a consideration in how we designed our systems. And then I'll briefly introduce interfaces and sort of what they do for us in AF and how to use them in an actor framework context. I will mention 2 use cases for interfaces, a couple of specific problems they solve to illustrate both how to use them and some further thoughts that I have. And then I'll wrap up with a conversation about something that I'm still kind of digesting as to what I think will be really, really cool and useful in Actor Framework going forward. So, I talk about architecture and actor systems a lot. And it's always good when I do that to go back to the elements of the actor model. And this applies to all of our actor systems. We've been doing actor systems for a long time. We've been doing actor systems pretty much since we got queues. right around the turn of the century. And yes, I feel old for saying that, but it's true. We've been dancing around this actor model, so it really applies to all of these things. This is an AF presentation, but what I'm about to say does apply to, AF, DQMH, Dr. Powell's system that he likes to use, all of these things that are multiple parallel processes that talk to each other. The actor model has three pieces to it. The actor itself, we talk a lot about those. That is our behavior and our data running in a process. The model also includes messages, which are the data that our actors exchange with each other. And the message transport is the third component. And we tend to dismiss that, or have tended to dismiss that as, oh, that's our queues. Okay, we use queues. That's our message transport. Okay, that's true. Doesn't go far enough. Actors themselves really only do three things, which is, I think, pretty important in understanding how our actor system should work. They really only do three things. If you stimulate an actor, it will send a message, perhaps, to somebody, another actor somewhere in the system. It may launch another actor, okay? Or it may change how it will respond to the next message it receives. Its internal state changes in some way. And I think that latter bit is what a lot of newer developers, I think, focus on. They look at the actors themselves and they think about designing them, and they think about how they change state. That makes a certain amount of sense. If you'll recall, the Certified LabVIEW Developers exam is typically answered with a queued message handler with an attached user event loop. That's one way to answer it, but very typical. So we're basically training our CLDs to think about those actors. That lends itself, I think, to a certain bias we have, given our niche in the general software world, of being very focused on the physical world. So we tend to be very task-focused. We think about the data that we have to acquire and the hardware we acquire it from. And you saw that in Andre's presentation. His example was based on some DAC hardware. So we may have that. We may have a database that we have to put data into or query in some way. And there's, of course, going to be some way for the user to interact with all this stuff. And so we think about our I/O, essentially. And then there's this piece in the middle, which I think gets sometimes de-emphasized. I'm speaking in broad generalities, obviously. And so I think that leads to designs for smaller systems. This works just fine. This is, by the way, the system diagram from the AF course. We'll have some leaf actors that tend to be that are focused on the physical world, doing whatever that business is, and then something in the middle. DQMH answers this really, really well. Actor Framework might seem like a heavy hammer for this, but I know from a great deal of experience that, for example, you can answer the CLA exam with an Actor Framework solution, and you can bang that out in 4 hours, often with time to spare. So all of our solutions work great in this space. They're all competitive. But I want to go back just a little bit further as I'm doing this exploration of the parts that we're missing. And I want to go back even further to the definition, the very definition of the actor model, which is that it's a model of computation, Jeff K's term, that treats actors as the universal primitives of concurrent digital computation. And it's that phrase, universal primitives, that I want to focus on a little bit here. Now, what does it mean for something to be a primitive in a model of computation? Well, here's a model of computation with something we can consider as primitives. They happen to be VIs. They happen to be doing something really interesting under the hood. But when you're using them, they're primitives. You don't think about any of that. This is the classic acquire, analyze, present LabVIEW paradigm that, my friend Chris Clark is nodding his head because we've been hearing this for 30 years now, right? But that's what it is. I'm getting a signal. I'm performing a calculation, and I am presenting the results to you. That is a feature. Start to finish, one feature. Get some data, show me the FFT on it. Okay? It is composed of our primitives, in this case some VIs that are VI lib that we don't ever look at, and then an actual bit of LabVIEW in the form of the waveform chart. But it's not just the primitives, It is their relationship to each other as defined by the wires that connect them, so the data that moves between them and the order that it moves. That defines the feature. Now, yes, in our actors, we often have a feature implemented at this level. Here's another example from the AF course. I'm doing a simple look at a process variable, do a calculation, and set the control variable. That's again, I'm just arranging some VIs using data flow to enforce an order of operations, and that's a feature. But in an actor system, there is a higher level of thinking. So this is a feature in the full actor framework, not inside of a single actor. And it is the same feature I just showed you 2 slides ago. I acquire a signal, I perform an FFT, and I push the results to the UI. The difference, of course, is that each of these is a parallel process. But note that the layout is the same. The feature is defined by my primitives and how data moves between them. Okay? We don't have a diagram in LabVIEW that does that. We do have a sequence diagram, which hopefully you're all familiar with. We do these less often in LabVIEW, I think, but I found them to be incredibly valuable for working through how my actors talk to each other. And you know, at the top, just a quick run through the diagram for people who might not be immediately familiar with them. Of course, at the top, I just have my actors in these blocks, right? Now, they could also be regular classes, but in this case, they're all actors. The vertical axis is time. It is unitless. As you go down the page, you're going forward in time. Here are my messages. They're just arrows, data moving between my actors. And then, of course, the blocks are just my methods doing the work inside the actor, which is intentionally suppressed on this diagram. Okay? A simple feature drawn out in a sequence diagram looks like this. Again, you see the flow of data between nodes, between primitives. A more complex feature has a more complex representation, but the idea is the same. So we can draw our features here in a sequence diagram. We can spec them out, define them, frame them. So in addition to the system diagram or the class diagram that we tend to use a lot, you know, this sequence diagram is also, or something similar to it, is also incredibly important. And they map back to the actor model, okay? We are, of course, still going to be talking about our actors and what they do internally, how their state changes internally. But now I can diagram out my messages and which actors send, an actor sends a message and it goes somewhere else. So my actors are producing messages. And the transport layer, which is not just the queues, it is actually all of those connections. That's the transport layer. Obvious when you think about it, but I think we haven't been talking about it in those terms. So let me give you an example of when you kind of look at an actor system at this level, just how your thinking might change. And I'm calling this example Dimitri's laser in honor of my friend Dimitri Sagatelian, who brought this question to Stephen Loftus-Mercer a few years ago, and I got to witness the conversation. Dimitri was at the time working on a system where he had a laser and a bunch of apparatus, and I don't remember what he was doing. That's his story to tell anyway. But the point is he had a laser, and he needed to know if it was safe to fire the laser. And if I recall correctly, I may be wrong, Dimitri, if you hear this, correct me if I'm wrong, but I recall that Dimitri likes mediators. He likes more direct routes. He asked the question, if I have to have this shutter open for the laser to safely fire, why do I have to report the shutter status all the way up to my top application, to the top of my application, which is really just a UI, in order to send it down to the laser? Why can't I just do this? Why can't I directly send the data? Why do I have to go through the tree structure? Why do I have to have the full topology? And at this level, I got 3 actors. It's really hard to justify why we would do this, why this is, by this little bit of inefficiency. It's not that inefficient, but it certainly feels that way. There's more work you have to do. Well, the problem, of course, is that we're not talking about a 3-actor system typically. We're talking about a lot more things going on. There are going to be several shutters in this system, We probably also want to know if the DAC is online and ready to acquire data for us. And the laser itself may be composed of several subsystems. The laser may not be ready to fire because it's not getting proper voltage and current. We have to check all of these things. So it kind of begs the question, because we don't want to pass all of that data to the laser actor. That's a lot, and makes the laser really dependent on everything around it, which is not the desired outcome. Why should the laser know about these things at all? And I think part of the problem, again, is it goes back to we tend to be very much driven by our I/O, by what we're trying to do in the physical world. We think perhaps not as much as we should about some of this logic in the middle. And I think the people in this room may think about it more, but I've talked to a lot of developers over the time who tend to think about the peripheries and not the center. The issue here, the issue with Dimitri's laser question, and it came out of the conversation, was a shift in thinking that has to happen. Dimitri's looking at this and he says, hey, I have to send my data, I have to send my shutter status all the way over to the laser. And that's not what's happening here. Dimitri's reporting a shutter status to his top-level actor. The top-level actor is taking that data and deciding, oops, I've got to go back, and deciding if he can fire. Okay? That's actually what's going on here. Not the same thing. It happens to be the same type of data. It's a Boolean, true or false. The shutter is open, we can fire. He might even be using the same message object, but it's not the same message. In fact, A has consumed that message in its entirety. And this has led me to add, we talk in a class about design principles, things that when you're designing actor systems of any kind, you should keep in mind. Things like our actors can receive any of their messages at any time and in any order. Or our actors are self-deterministic, messages are requests, never commands, right? I want to add a third to this. With rare exceptions, and ironically enough, I will share an exception with you shortly. With rare exceptions, actors don't forward their messages. They consume them in their entirety. And then they make a decision, and then they issue possibly a new message. So what's going on in Dimitri's laser is more like this. Over here on the shutter side, I'm actually looking at all of my shutters. Are all of my shutters okay? That's one Boolean, not three. Okay? Is the DAC also online? And if it is, therefore my whole beam path is on. That's the decision that was made at that point. The beam path is ready to go, right? The laser is actually getting enough voltage and current. All of that is percolating up to some more centralized position in the system, maybe the top level, maybe somewhere else. But that somewhere else is making the decision that we can fire. The laser is just a component. So when we recognize the importance of some of these middle decision layers, we can start to go back to our topology. This is the part that I was thinking was missing, and start to evaluate the topology itself. There's information in the structure of our actor systems that drives how our actor systems work, and we really want to take the time to understand that and use it and leverage it to our advantage. So if I've got Dimitri's problem here, and I really, truly, legitimately am just passing on a piece of data from B directly, and I want to C, and there's really, and A doesn't care about that piece of data at all, the question I should ask myself, and it's a question, this is not a directive, it's a question to ask. Should I change that structure? Should B be the nested actor of C? Yeah, maybe, maybe not. There might be other reasons, but that's something to think about. Maybe B does actually interact with A in a meaningful way, and not simply as a pass-through, while also just sending something to C. So a question to ask myself is that actor overloaded? Should I split it apart and have a portion that talks directly to A, interacts directly with A, but then I have this B prime that's a nested of C? Maybe that's right. Here's a personal favor, and I had this one show up in an AF course on-site with a customer. You know, everybody, lots of folks have invested time in publish subscribe for actors. I have an actor that will publish data to lots of destinations. I've written these myself, okay? The question that I would ask if that's really, if that routing is really a burden, why is C at the bottom of the hierarchy? Maybe we acquire data at the top and fan it out to a bunch of subordinate processes. Maybe, right? In a complex hierarchy, you're going to be making a lot of trade-offs. But these are the kinds of questions we should ask because there's more to the actor model than just our actors. The messages in the transport layer matter, and they deserve our attention as much or perhaps more in some cases than the actors themselves. And we have to accept that our topology is going to evolve as we learn more about our system. Right? That is the piece that I think we haven't necessarily talked about enough, and I'm starting to talk about more with folks. GDevCon NA back in October, I need to talk to Darren Nattinger about this. I need to run it down, but he actually he was managing state just in the relationship between his actors, and I haven't had a chance to follow up with it, but I thought that was really cool. I want to see how he did it. Okay, so in parallel with thinking about all of this, we get interfaces. Okay, here we go. Game changer. I do not have the luxury of the time to walk through interfaces with you. Show of hands, I will be curious, who has had a chance to work with interfaces and kind of digest how they function, even if they're not using them in your code yet? A fair chunk of you. For those of you who are not familiar, I apologize, don't have the time to do a deep dive. On my Vimeo page, link at the end, Stephen Loftus-Mercer and I did a joint presentation back when interfaces first came out about how they work. Stephen did another one at NI Connect, which came at it from a slightly different approach, and I thought might be more appealing to a lot of people. If that video is available, go look those up. Stephen walks you through it and really nails it down for you. Suffice to say, for our purposes here, what an interface is, effectively, is an adapter. Okay, I can take a class with core behavior. I'm showing a couple here, right? I've got rotating tools like screwdrivers. I've got impact tools like hammers, right? And I can create an additional adaptation, additional methods for that class. And then I can apply those through by inheriting from both the core behavior and these interfaces, I can apply that additional behavior to a set of classes, and now I can use them in ways I wouldn't normally have used them before. And I can use disparate things in the same way, like a house key and a screwdriver and a hammer, all different kinds of tools, but I can pry open a paint can with any of them, right? That lets this kind of code arrangement, makes this kind of code arrangement possible. Same hierarchy on the left, just shown to you in the LabVIEW class hierarchy window. On the right is my screwdriver, my hammer, and my key. They are all levers. I do have to do the two more specific class to make this work, but I can do that. I can cast them to all be levers, and once I've done that, now I can apply what I should have labeled it as the pry function, but I can apply the pry function to all three of these classes. That's, in practice, what we can do. It's an adaptation. I can now use this tool in a different way. Now, how is this relevant to actors in Actor Framework? Now I'm getting Actor Framework specific. Actor Framework actors are just classes. Therefore, an actor can implement or inherit an interface. What does it mean when that happens? Well, the AF tools support creating messages for the methods of an interface, right? And we get something that we're calling an actor interface, cleverly enough, right? That we don't have a tool yet, and I think I was just talking to Casey May, we might do something with the AF Guild to write a tool to do this for you. Right now you kind of have to do it by hand, but if you go ahead and make a library for your interface and you drop an interface in there in the usual way and then create methods for it as you expect, then when you use the AF tools to create messages, they all get dropped in your library for you. They appear where you expect them to be on disk. Life is good. You have, in a folder, in a library in your project, a little package that is your actor interface. Now, what can I do with that? Well, doing that is functionally equivalent to doing this. So here I have, instead of an interface, I'm using an abstract parent class. And it's a trick we do a lot in Actor Framework. Anywhere you want to do, you want to have dependency injection. If I want to change out, for example, the different cooler panels that I have here, I create this abstract parent class called panel in this case. And it is an actor. It has methods. The methods are all dynamic dispatch. They don't do anything. They exist to be targets of messages. And then any child of the abstract parent can receive, without crashing out, any of the messages of its abstract parent. Okay? Interfaces are functionally equivalent to that. So if I declare that an actor inherits this actor interface, it can now receive all of those messages, and I can override their the dynamic dispatch methods and populate them with actor information. That's what we do with that. So, what are the use cases for this? And I'm bringing up these two specific ones because they kind of lead into what I want to talk about later. But a couple of them are improved dependency injection. And Anton spent a little bit of time talking about that, and I think he's probably saved me a couple of minutes on my presentation, which is great, fabulous. Really appreciate that because I'm kind of tight for time. Improved dependency injection. I wish I had my preview, I don't. What's my next slide? Okay, so let's say, actually I'll go back one. What I have here is I have, my cooler is launching an actor that implements the panel interface. That's what's going on here, okay? I have my original cooler panel, and then I have this thing over here called an actor stub for UI. Well, what is that? So let's say that I want to do, as Anton was suggesting, and I do this all the time, fabulous presentation, Anton. I do this all the time. If I want to take an actor and I want to prove out that it sends a message to its nested actor, well, we worked really hard in Actor Framework to make it kind of hard for you to intercept that message. So the way around it is we use a mock object that is a redirector, just like you saw earlier this morning. And so if I stimulate the actor under test, it's going to send a message to what it thinks is its nested actor, which in this case is just going to send it right back to me. And then I can prove that I've sent this message, pass my unit test. Okay? How do I do that? As I showed, if I'm using abstract parent classes, I can do this, right? And I'm going to go ahead and make a child of the panel, call it my UI stub, and I'm going to override receive message, which is rarely used in production code, but I think often used for this purpose. And the receive message just does the redirection for me. Now, I have to do this if I'm using an abstract parent class. I have to do this for every place that everything I'm doing here, like cooler panel or anything else like it, where I'm doing this dependency injection, I have to make a stub. That's not a big deal at this level, because the override of received message is very simple. And I can either just cut and paste from one block diagram to the other. This is something that's simple enough. I could also probably script it out pretty quickly and just have a tool that did it for me all the time. Not a big deal at this level. But what if I'm doing something more complex? What if I'm replacing my local cooler panel with a remote proxy that lets me have a cooler panel somewhere else, right? That gets more complex because if I'm talking about something like a TCP connection, that's a hell of a lot more complex than a simple redirect. I've got to do all the TCP work, and I have to manage the connection if it comes and goes, right? Because it's probably not a persistent connection. And I got to manage all of that. That's some work. That's code that I would like to write once because I write a lot of these proxies. I'd like to write that code once and be done and then inherit from it. But I can't. Because if I want to do unit testing, and oh boy, howdy do I want to do unit testing with mock objects, I have to inherit for messages. Okay, this is a real-world example from a project I finished up last year. I had 9 different proxy connections with 6 proxy actors, and every time we touched the connection code, I had to touch it in 6 places. It was a trade-off I was happy to make because unit testing was why that project succeeded, because it was a complex project. But boy, did I resent every time I had to do that. Okay, fine. Interfaces solve this problem for us. I told you just a moment ago that these are functionally equivalent, and that is not strictly true. Okay? The principal difference and the principal value of the interface is that I can do this instead. I can write an actor stub class with the override of receive message, and you can see it up there. So that's my redirection. And then whenever I want, and I can use that everywhere I need to do a redirector, one of these actor stubs. All I have to do to make a new actor stub is just, I make a new actor class. I make a new class. I make it inherit from panel. I make it inherit from actor stub. Done. 11 mouse clicks, and I type the phrase actor stub for UI. That's trivial. Probably also scriptable if I really felt the need. In fact, it would be easier to script. So that's really cool. Remember that, we'll come back to it. It solves this problem, right? Because I can do the same thing here. I can take a connection manager and I can declare that I've got a UI proxy that inherits from panel interface. Done. 11 mouse clicks, out the door. Hold on to that thought, we'll come back to it. The other thing it lets us do is it lets us kill abstract messages. Who here has written abstract messages? Who here likes abstract messages? Yeah, one guy likes them. Yeah, you know what, abstract messages were my idea. Everybody hates them some abstract messages. I have seen customers go to great lengths of self-harm to avoid using the abstract message because they are confusing. The interfaces let us, as of getting interfaces, abstract messages are deprecated. They're still supported because you're going to be dealing with legacy code, but don't use them. And if the next few slides make no sense, don't worry about it because you never have to deal with them again. But abstract messages solve a very real problem for us in Actor Framework. It's why they were there. They were necessary. Actor launches nested actor, right? That's a static. There's a static link there. You've got the nested actor as a cube on your block diagram somewhere. So the caller actor is static linked to nested. Can't avoid it. Nested actor wants to send a message back to the caller because we like to do that. So the nested actor reaches out to the caller's library to grab a message, and now I have a circular dependency between my libraries. Who here likes circular dependencies? No one, because you're all smart. Circular dependencies are bad. The most obvious problem in terms of writing the code is that you can never use this nested actor by itself. You always have to use it with that caller. Sometimes that might be okay. You've bought some technical debt if you do that, but it may be okay. You may be able to get some loan forgiveness there. Most of the time, though, it's terrible. The other thing it does, and this is a little more surprising to people, is it can really harm you when you're loading a project. Project load times go up when you have these kinds of circular dependencies. Builds become more difficult or sometimes fail because of circular dependencies. It can really screw up writing PPLs, okay? Lots of reasons why this is terrible. We really need that to go away. Abstract messages solve that problem by doing dependency inversion, right? We just said, okay, fine, we're going to make this thing called an abstract message, and that is going to be the parent of messages that our caller actually receives. But the abstract message class lives in the nested actors library. When we do that, notice that message inherits from abstract message, the caller is calling the nested actor, everything makes sense, all of our arrows point in the right direction, right? And therefore, no dependency. If this slide doesn't make any sense, don't worry about it. Abstract messages are gone. I'm just letting you know that this is how we solve the problem. It did still, the way we did it, though, did leave us with a little bit of a dependency issue, which is that, if I have an actor here that has some messages that inherit from that abstract message down there, and I have this caller library wants to send my middle actor that message, well, guess what? Now it's linked down to that nested actor, and that's not so good either. The answer there, this was a mistake that we made because we tied abstract messages to the sender, because we should have pulled the abstract messages out into their own libraries. And I was advocating for that in 2018, 2019. Here I'm going to have some interfaces. I don't have to do that anymore. Because interfaces do this. Actor interfaces do this. All of my stuff is now in a separate library. The caller depends on the library through inheritance. The nested actor depends on the library through static linking, but that library is separate. All my arrows point in the right direction, and we're happy. No more abstract messages required. All right, so where does that leave us? That leaves us with going from this actor library, which had the actor class, all of our standard messages for this actor, child messages for that actor, if those are messages that inherit from abstract messages somewhere else, and our own abstract messages that we send to our caller. Well, now we do this. In most cases, there's no longer a need to even have a library for the actor, unless it sends some messages to itself, right? But there'll be a lot of actors that don't, and therefore don't need to be in libraries even. But the actor is going to inherit an interface. That's the messages it receives. It's going to invoke messages from a different interface, and everything's nice and separated out the way we like. Now, I do get a question. The question is of interface granularity, and I had to have a few discussions about this myself to really understand why. How many interfaces should an actor have? It's really tempting to look at, if we're going from on the left is sort of a pre-interface view to going to the interface on the right. It's really tempting to go, yeah, abstract messages are gone, and so I think I should just take all of my messages and make them part of an interface for this actor, because after all, these are the messages it's supposed to receive. Sometimes that's okay, usually not, because consider down here I have this dual fan actor, which basically runs a fan until it fails, and then it runs a different fan. And I might decide that code's really cool and I want to use it somewhere else. So I'm going to go use it on a motherboard. Well, if the motherboard is going to receive that update fan status message, guess what? It has to implement that interface, which is, of course, statically linked to dual fan. That's why it has to use it. But that's going to give me two completely irrelevant messages. There are no pumps on a motherboard, I hope. That would be weird. Some steampunk people, maybe. Don't want to do that. So the important thing to understand here is that really what that adapter is, what that interface is, it is how a specific actor X sends messages to a specific actor Y. Okay? And if I have 3 different actors all talking to my cooler, that is going to strongly suggest that I'm going to want to have 3 interfaces. Okay? Now, it happens for this example that every single one of these had just a single message. That is not what I'm saying. Have as many messages, dual fan should have as many messages in that interface as needs to be for all the messages that dual fan wants to send. But it should only be the messages coming from dual fan. Okay? How actor X talks to actor Y. Now, with that in mind, that's mechanics, that's tactics, that's solving the problem that shows up in your inbox on Monday morning. What does this mean? What can this mean for the designs of our system? Let's go back to the transport layer, which we don't talk about very much because it's just the queues, right? No, there's more to it than that. Here's the topology for a part of the cooler project that's just our UI stuff, right? I've got, I'm not showing the actual cooler panel, but it would be there. I am showing the actor stub. I am showing a UI proxy that is a connection manager that takes messages, right? Okay. I'm going to make it, and this is my cooler, which I've been showing you this whole time. I'm going to make a change here. And I'm actually going to split the cooler up. I'm going to give it a parent actor. The parent actor implements a generic level control algorithm. Think the thermostat in your room. Okay? But that's an algorithm I want to use again and again and again. And cooler inherits that. And it inherits a send-point device. And it launches something that answers to the panel interface. Now, let's look at what we have there. This is the thing that excites me. This is the thing I'm still processing in my head. Look at this. Here's the actor model again. Here's my diagram. I actually have specific artifacts, like I've always had, specific artifacts that are the actors in my system, the things that change state internally. My level control, my actor stub, which is just a redirector, my connection manager. That's all internal state, core behavior, if you will. I have distinct code artifacts for my messages. My messages have an actual, they're not tied to the actors anymore. They don't have to be. They can be. You might choose to. But they don't have to be. I can have a thing. It's just, here's a body of messages that I've defined for my system. Regardless of what else is going on, these messages are going to move around. And I also have, they happen to be actors, but the role of these actors is specifically to define what my topology is, who gets launched by whom, and which messages are supposed to receive. Okay? This is like the ultimate Lego. I can take my actor system apart into just these sort of basic pieces here. I've decomposed the system to a really fine level. The design aligns with the model now, or can align very closely with the model. I can have all of my actor interfaces defining all of my data and all of my messages. I can just write the library. So I can have somebody write the library for me, right? And be done. There's a little topology in there, as I said, because it's actor X talks to actor Y. But they move around pretty easily, right? Behavioral actors, state change actors. These are the things that change state, that do something internally. The thing that my most successful reuse code ever was network endpoints, which don't take any messages because you can use it in any system because they don't take messages. We have that. We can separate that out now. And then we can so our core behaviors. And then we can have our transport layer defined by a set of actors, right? That's relationships and contracts. That's the structure of our application. And the structure is defined entirely separately from how we actually implement it, how we actually solve the problem. I don't know where I'm going with this yet. I don't. I don't know how far I should take this, honestly. But I think the actor framework has always promised reuse. And we've always had that barrier of, I've got messages that are specific to my system. I have relationships that are specific to the actors. I don't have to have that anymore. So I think we're going to get more reuse out of our core behaviors because we're going to be writing messages they exchange and the relationships, and then we'll be plugging these in as we need it, right? We're going to be able to revisit the topology as it needs to evolve, as we find opportunities to make our features better, right? I've got a feature laid out as all three of these things, and I can move them around a little bit to get the most efficiency I can. So I can avoid some of those really long hops, for example. So I can take advantage of some of those relationships. And that's what has me really jazzed. I mean, yes, interfaces are cool at a tactical level. They make my life so much easier while I'm working. But when I'm thinking about design, this is what I think is really cool. And I don't know how far to take it yet. We'll find out. So I'll take some questions. This is me. This is how to find me. Look me up on LinkedIn. Reach out. Everybody's invited to do so. Let me know you saw me here. So, because I get a lot of requests. Website, that's the Vimeo channel where you can go see Stephen's presentation on interfaces from 3 years ago. And of course, Actor Framework Guild. So I have 2 minutes and 23 seconds.